This is going to show how to do linear least squares. We're going to look at a very simple example, and we're going to emphasize how we can turn this into geometry and something that we can use with the dot product. So we're going to start over here on the left, where we have three data points. X values are 2, 4, 7. Y values are -1, 3, 4. And we want to fit a straight line. These aren't really a linear function. It's not really a linear relationship between y and x, but can we fit something that's relatively close as a linear function? Well, I've got an example here, and I've got some sliders. I've just got mx plus b, and I could try to fit that by hand. I could take the intercept down. It looks a little better. Maybe make it a little steeper. That might fit the first two better, but maybe a little less steep. A little tricky to figure out exactly what's best there. And in particular, how would you even define what's best there? Well, what we can do is we can look at the red dots, which are the prediction of this model with any particular choice of m and b for the y values corresponding to our given x values. I have it set up to automatically calculate those here in the table. And then we can compare those, the predicted y value to the actual y value, and say on average they should be close. And one clever thing to do is if we look at the sum of the squared differences between these, that's going to connect to geometry and calculus and dot products and all kinds of good stuff. Because it's essentially a Pythagorean combination of the errors. So in Desmos notation, I made a list which is put the x values into our function, and we'll practice this with the Desmos, but the main thing is not the notation right now, to get these values z as the predicted values. And then I am comparing them. I'm looking at the squares. So this each individual for any particular n, this is an error. I look at the sum of the squared errors. And I've got it down to a 2.83, and honestly, I don't think I can get it very much lower, but we're going to see how the algebra predicts exactly what the best m and b are going to be and exactly what the smallest possible error is going to be. So that's where we go over to the right here. This is really, secretly, this is projection onto a plane. It happens to be in 3 dimensions because there's 3 data points, but the algebra that we set up, and this is stuff that we talked about in class, the algebra we set up works absolutely the same for any number of data points, and really we're doing projecting onto a 2-dimensional plane in n dimensions there. So what we're going to do is we're going to define a vector for the x values, 2, 4, 7, a vector y for the y values, -1, 3, 4 here. We're going to have a nice little helper vector, 1, 1, 1, and that's to deal with the constant term. And then an elegant way to say the z's are what happens when you put the x values into the function mx plus b. Well, I put the vector x, which contains the x information, multiply by m. I take my constant b, and I need to promote that. I need to give that, have that give a value for every single entry here, every x value. Well, it's going to give the same value, so I just multiply it by this helper vector 1, 1, 1. Okay, so that gives me z. So this is a vector language where I was using more of a function language over here. Okay, so just to unpack that, like the first z is going to be m times x1 plus b times 1, or in other words, mx1 plus b. That's exactly just saying z equals mx plus b, but in a vector notation. And even though these three just have 3 components and we can picture them in 3D, if it had 17 components, the algebra won't really be fundamentally different. Okay, so what do we want? Just going very briefly through the derivation that we did in class. We want the difference, the error between the actual vector y and these predicted values z. We want that to be perpendicular to both x and a. And that's because we're picturing this. Let me bring up another picture. We've got a plane, and I went ahead and put in this plane that we've got, and we're picturing this as taking the point that's in 3-dimensional space that's representing all of our true data values, and we want to project that onto the kinds of data values that we can actually create in an mx plus b form. That's exactly things of the form m times the x vector plus b times the a vector. That's exactly this plane. So we're just projecting it onto the plane. So that's a cool thing, that this what seems to be a statistics problem of approximating data by predictions really can be thought of as a geometry problem. There we go. Okay. And we'll say a little bit more as well. We didn't get to the full kind of cool geometry of that in class, but we want to think of this as the projection problem. How did that work when we recognized that our projected value, this z is what we were calling p in class, is just anything of the form mx plus ba. We distribute it out, and this should look very familiar. This is how we're going to, we had C1 and C2 because I wanted just generic coefficients in class, but here they specifically have the roles of m, the slope of the line, and b, the intercept of the line. So let's put that in. Here, x dot x, just going to be this dotted with itself, turns out to be 69. We're going to need a dot a, that's easy, that's 3. We're going to need x dot a, that's pretty easy, it turns out to be 13. And y dot x and y dot a, if we do those calculations, we just get this. So this is what we usually do. We don't necessarily go further. We could have gone further and tried to go ahead and get master formulas for m and b here. They're a little ugly, and so it's usually not a bad idea to just stop there and actually put in the numbers and then solve it. So let's see, how do we solve things like that? Elimination is usually your best tool. You could do it by substitution, but elimination, let's say I'm going to multiply the top equation by 3 and the bottom equation by 13 so that the b's match. Then I'm going to subtract those equations. So the point was now that the b's are going to cancel out. 207 minus 169 is going to be 38 times m. 114 minus 78, if I did it right, 36. Yeah, that's right. And when you divide, it simplifies a little bit, but we'll probably just go ahead and go with the decimal, just a little bit under 1. Then once you have a value for either variable from that elimination procedure, you can just go back to either equation and solve. The numbers are slightly simpler, so I went back to there. And we get b is 6 minus 13m over 3. That's just from this bottom equation up here. And when you actually calculate that out, it's about minus 2.105. Okay, so our prediction is that the line, here we are, it's right here. The line is 0.947x minus 2.105. So let's put that in. We'll see what it gives us as the total, that total squared error. But then I'll show you just calculating that out as well. So 0.947 and minus, so I have the minus 2.1. I did not put that in on purpose. I did not even remember that that was the ideal value. So we were pretty close. And this is saying that you get a squared error of 2.63. I claim that's the smallest possible error because when you project something onto a plane, you're finding the closest point on the plane to the point that you started with. And we'll review that a little bit in terms of the geometry in class. So our predicted values, okay, what are those going to be? Well, remember I had Desmos actually calculate those. I also just can multiply our newly found m times the x vector plus our b value times that 111. It's just basically evaluating this for 3 different points, just in a vector language. And we get these 3 values. Notice that minus 0.2, yep, about 1.68, yep, and about 4.53. Those are the heights of the red dots. And if we actually just plug it in and get exactly what that minimum squared error is going to be, and that has some nice uses besides just being something we want to make small in order to figure out the best m and b. We plug that in. Oh, and I'm getting a different number. That's interesting. I probably made a mistake there. Let's see. Oh, that's a +1. Aha. Okay. That should have been a minus 1. And let's see if that gets us a better answer. Yeah, 2.65. Okay. Okay, and so that's going to be, in a nutshell, our process. And the cool thing is, even though we related it to some intuition about what three-dimensional geometry is going to look like, these equations, this idea of the dot product being equal to 0 to determine a projection, that works in any number of dimensions, and nothing else depended on there just being 3 entries in these vectors. So it's going to be very powerful.